Hey people! Today we are going to get into patterning, and in doing so we are going to represent a pattern in three different ways. Based on this expression here, 3x minus 2, we are going to represent this expression using a table, a t-table, and a graph, and we're going to take a look at the relationships between all three of these things to represent the same pattern. So first thing I like to do is I have my expression here. I'm going to represent it in the t-table, and I've written down my x values, and I say x values, those are your term numbers. I say x values because it actually represents your x axis, your horizontal line in your graph. So -1, if you were to draw an ordered pair, that would be right here, 0, 1, and 2. But to get my y-axis value in my t-table, or my term value, I actually have to use the expression to figure that out. So what I'm going to do is I'm going to substitute -1, since this means x. In my expression, there's my x value. That's my variable. As you all know, variable. It's your unknown. So my -1 is my variable. I'll substitute it there, and I'll solve the expression to get my y value. So I'm just going to write it as an equation. So to get my y value, I have to use the expression. So 3, and x becomes -1 minus 2. So we have some integers here, multiplying subtraction using the BEDMAS rules. Of course, you're going to multiply first. So 3 times -1 is -3. Then we have subtract 2. Using my integer rules of subtracting integers, I add the opposite. So -3, this becomes plus, and that 2 becomes -2. And now I have -3 plus -2, which is -5. So this right here is actually -5. Now 0. So to get your 0 value, you do the same thing. You substitute your x value for 0. That's your variable. And I fill in my equation. So 3 times 0 is 0 minus 2. Now, most of you can do that in your head. That's 0 degrees. Then you go down 2 degrees, it's going to equal -2. Or you can use the rule, so you change this as an addition question, and that 2 becomes -2. And then you could use the rule to figure out that your answer is ultimately -2. So for my 0 term number, or 0 variable, or x, my y for that ordered pair would be -2. All right, now if I have my x value as 1, I substitute x for 1 minus 2. 3 times 1 is 3. Now we're done with the integers. This becomes very easy. So this y value here will be 1, and then 2. So I just substitute that x for 2 minus 2. So 3 times 2 is 6 minus 2 equals 4. So now I've completed my t-table. And now I got all my ordered pairs, and now I can put my ordered pairs on my graph. So I'm just going to actually change the color here. Let's put it to red. All right, so now -1 and -5. You always plot, remember, your x value first when you're graphing ordered pairs. Ooh, itchy nose. So -1. Which is right here, and -5 is my y value, so I go down to -5. So that ordered pair is right there. My next one of 0, -2, so I stay at 0, which is my origin, and I go to oh, what happened to that one? All right, so it's fixed up now. So 0, -2, my next ordered pair is 1, 1, so 1 going across the x-axis, then up 1 along the y-axis. There is my third ordered pair, and then I have 2 and 4. 2, 1, 2, 3, 4, up the elevator I go, and there is my fourth ordered pair. And then I'm going to draw this freehand, but of course you would be using a ruler. That's not good enough. All right, sorry about that. So I just fixed it, and I actually just used an object tool and inserted my my line here, connecting the dots. Now, a lot of people might be wondering, well, why did I extend my line? And we're extending it because this is called a pattern. And in patterning, we want to be able to make predictions. So because it's a pattern, this is not the starting value or the starting term number. This is not the finish line. You could actually extend your line to make predictions. So for example, if I wanted to know based on my t-table here, what would be my third term, yeah, I could just simply extend the t-table down, or I can use the expression, but I could also use the graph to make that prediction as to what my third term number value would be. So for example, if I were to do that, I would go across to the 3. That would be my term number. If I were just to write that down here, so let's say my term number would be 3. I would just take a look at where my line actually intersects. So at term number 3, my line is actually the value of 7. My y value would be 7. So I could extend it here. And as you know, if you were just to use the t-table, the pattern is, as you can tell, is add 3 going down this column here. So you keep adding 3 each time. So you can just add 3 one more time to get 7. The fourth term, the value add 3 again would be 10, and so on. You could also go the other way. So -1, if you wanted to find the term number of -2, well, if I were to go back here, -2, I go down, 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 down until my line intersects, which is at -8. So my -2 term number, the value would be -8. And of course, once again, we could also solve that using the expression. So again, if I wanted to use the expression to find this third term, yeah, we know the answer here is 7. Yeah, we know the answer is 7 here. But quickly using the expression, you would just substitute the x for your third term to get your y value, or your term value. -2. So 3 times 3 is 9, -2 equals 7. And again, the same idea, if I were wanting to find out for the term number -2, I'll do that over here. So y equals, my expression is 3x minus 2. So I substitute x for -2. And as you can see here, ultimately we should be getting an answer of -8. So 3 times -2 is -6 minus 2, which is the same thing as saying adding the opposite. So -6 plus -2 is -8. Boom! There you go. That's my answer, -8. All right. Now there's also a couple other things that I want to just quickly go over here. I mean, as you can see, we've using a table, we see a pattern using the expression, the t-table, and graphing it. I just went over how you can take an expression and create a t-table, but can you do the reverse? If you had a t-table, can you create an expression, so 3x minus 2, from a t-table? And the answer is yes, of course you can. I have right now something very unique written down here in red. And I don't know, but can you make the connection here with the expression? Basically, if you had the t-table already solved and you got all your ordered pairs, if you notice this relationship down here, if you can figure out that relationship or that pattern, which in our case it's adding 3, you're adding 3 each time, that actually becomes, in your expression, the coefficient in your expression. So if you know that pattern, that automatically becomes your coefficient. Now remember, your coefficient is always the number that you're multiplying your variable by. So you write down your expression, 3x or 3n or whatever letter that you want to use. Now to get your constant, that's what this would be, this -2 would be your constant. And of course, x would be your variable. How do you get -2 from this table? Well, all you would have to do is you substitute one of your x term number values for your variable. I like using 1. 1's easy. So I substitute 1 for n. This would be 3 times 1. Well, that would give me 3. Well, what else do I have to do to get back down to 1? Well, if I have 3 times 1, which is 3, in order to get down to 1, I would have to subtract 2. And that's all you would have to do, subtract 2. And if I want to prove this relationship again, well, let's try it with a 2. Let's see if by doing this, will I get 4? And I know we solved it already, but I'll just go over it. So if I were to substitute n for 2, it'd be 3 times 2, which is 6, minus 2 equals 4. So that there is definitely my expression, which we already solved, by the way, up there. By the way, don't forget your constant. The reason why it's called a constant is because this value is always there. It's constant. It's always happening. So if we were to continue to solve this, substitute 1, 3 times 1 is 3, you're always having to subtract 2 to get your term value. You always have to subtract 2, and that's why it's referred to as the constant. That is always there. It's never changing. Whereas the coefficient does change because you're multiplying it by your variable. Now, one final thing I do want to go over is this here linear pattern. The linear pattern, the reason why it's called, this relationship here is called a linear pattern is because it's a straight line. It's linear. And anytime you see this type of an expression or an equation, so y equals 3x minus 2, where you have a coefficient and then you have a constant, this type of expression does mean linear pattern. Okay. Now there's a couple unique things. This -2, we've already made a few connections between these three strategies, but there's another connection here as well. This -2, if you take a look all the way here, look where your line intersects the y-axis. The -2 means where the line intersects the y-axis, and there's actual term for this. It's called the y-intercept, which is basically, again, where your line, your linear pattern, intersects the y-axis. Your 3x is actually referred to as the slope of your pattern, of your line. And if you were to take a look at each dot that we've written down, as you go up a term number, you're going up a slope of +3. You increase a term number, you're going up a +3. Term number 1, you go up a slope of +3. And take a look down here, and again, there is that +3 relationship. There is the +3 relationship. All of these three things connect with each other. Isn't that awesome? Your graph, your expression, your table, they all connect to each other. And in the next video, I'm going to actually show you how you can modify these linear patterns, and you'll see how the slope changes, the location changes, how you can go down with negative slopes, and so on. So anyway, there's some connections between tables, expressions, and graphs.